This podcast is going to teach you about the concepts of buffering capacity and how one can prepare a good buffer. The reason why you're watching this is that you will have to prepare a buffer in the lab on block day. So to get ready to do this, you need to search in your notebook for about a 2-page handout. That was kind of a helper lecture outline we've been working on about buffers. And find the page that starts with the words buffering capacity. You can pause the podcast to go find that sheet now. All right, I'm assuming you found the sheet, and what you're looking at hopefully mirrors what you see on the screen. The buffering capacity of a buffered solution is defined in terms of the amount of hydrogen or hydroxide ions that can be absorbed without seeing a big change in your pH. If you have a buffer with a large capacity and has large concentrations of the components of acid and anion in that buffer, then that's going to be a good buffer. It's going to be absorbing any challenges that you might put to it by adding, say, a strong acid or a strong base. So the pH of a particular buffer solution is almost completely determined by the ratio of the base over the acid. I need you to get comfortable with it. Right here you can see A with a minus. Sometimes they call that base, sometimes they call that salt, sometimes they call that the anion, but it's the conjugate base of the acid that you are using. And the acid that you're using is symbolized with HA. So the capacity of your buffer to act as a great shock absorber is determined by the magnitudes of the concentration of your acid and the concentration of its conjugate base. So following along on the handout, you will see a problem that says calculate the change in pH when you add 0.01 mole of gaseous hydrogen chloride, hydrochloric acid, to 1 liter of the following solutions. And at first they look very similar, but you can see that in solution A, we have 5 molar of acetic and 5 molar of acetate. Just ignore the sodium, it's a spectator. But in solution B, you can see we only have 0.05 molar of each of those components. So what we will do now is take a moment and don't write until you look at the explanation. Then you can pause the vodcast to copy this information down. So I set up an ice chart here. And why am I putting the acetate first? It's because in the problem they challenged you with an acid. So you got to put the guy first that's being attacked by the acid, and that's the base. So acetate and hydronium or hydrogen coming from the hydrochloric would turn it into acetic acid and water. And I'm going to have my Henderson-Hasselbach equation up here because I'm going to use that guy too. So if I start with 5 molar in acetate and 5 molar in acetic in my buffer, somebody dumps in 0.01 molar of hydrochloric acid, you will lose 0.01 of the acetate, very small change. All of the acid got neutralized, and the acetate increased a little bit. So I go pH equals pKa plus the log of the base over the acid. The negative log of 1.8 times 10 to the minus 5, that's the pKa of acetic acid, but you already knew that because you've memorized it now since you used it in about 20 problems. The pKa is 4.74. But here's what's so cool. If you take the log of base over acid, that's essentially 5 over 5. That's essentially the log of the number 1. And the number 1 is 10 to the 0. So anytime you take the log of 1, that equals 0. So essentially, your pH would be 4.74 plus 0, and there's no real change in your pH. So that's kind of cool. I put that up over here too, although I got kind of cut off over on the upper left. When you take the log of your base over your acid, then that's a 0.5 over, that's a 5 over 5, and this is 0.5 over 0.5. Those are both the log of 1 and are equal to 0. I set up a nice chart for the second solution B, but now I have tinier amounts, 0.05 of the acetate, 0.05 of the acetic, and I'm still challenging it with the same amount of acid. We still neutralize all the acid, but there's a lot less left of the acetate, and we have an increase of 0.01 molar for the acetic acid. So I'm going to go pKa, which is negative log of 1.8 times 10 to the negative 5, and that's where the 4.74 comes from, plus the log of 0.667. That's 0.04, the base, over 0.06. That's where that came from here. And essentially that got cut off a little bit as well, but it's showing 4.74 minus a 0.18. That's what's missing from right here. And so my pH is 4.56. If I wanted to summarize the differences in these two systems, we did have a change for solution B, although it's pretty small. And that's because solution A had much greater concentrations of the acid and the base, so its pH was essentially unchanged. That means it had a greater buffer capacity. The solution B changed by about 0.18 on the pH scale. So I hope you understand buffer capacity. It's not too difficult to understand, but what we also need to understand is how to create a buffer that's going to be the best shock absorber, not only having good buffer capacity, and this is going to be dependent upon the pH of the solution that's required. So we're looking for a solution that is the most resistant to changes in pH. So if you have large changes in this ratio of anion or base to acid, you'll get large changes in pH, and we want to avoid that. So what we've come up with is an understanding that if you have your acid concentration roughly equal to your base concentration, that's when you're going to get optimum buffering. When you have that ratio roughly equal to 1, then you get this. When the pH is equal to the pKa, because remember the log of 1 is 0, that is going to be the most effective buffer that you can create. This is the one that will be most resistant to change. So your goal is to get a ratio of base to acid as close to a 1-to-1 ratio as you can. And if you know the Ka of a weak acid, the pKa of the weak acid can be used to determine the ratio that you'll need to find. It's way simpler than it sounds. Let's look at an example. The first thing I want you to do in this problem is to look at this list of 4 weak acids. We want to make a buffer that will have a pH of 4.30, and these are the choices that we have available to us. Remember, the word salt is just the same word as the meaning as the word base. So take your calculator, pause the vodcast in just a moment, and take the pKa of each of those acids. That is the negative log of the Ka. And write your answers down next to the Kas. When you're done, turn the vodcast back on and check your answers on the next slide. So go ahead and stop the vodcast now and do your math. All right, I assume that you had done your math, that you're not just getting the right answers there, because unless you actually touch the keys on the calculator, you don't get the muscle memory of how to get a pKa. So here are my answers, and we might differ slightly, but I hope what pops out at you is that the benzoic acid with benzoate ended up with a pKa that was the closest to 4.3. Remember, that is our desired pH. So the next slide is going to show you how you can get the best ratio of the base to the acid to make an effective buffer. So what you're going to do is rearrange the Henderson-Hasselbach equation. And I've written it here. pH is equal to pKa plus the log of the base over the acid, the benzoate over benzoic. Well, all I want to do is try to get the pH, the pKa off of this side. So I'm going to subtract pKa from both sides of the equation. Then I kind of flipped it over to make it fit. So ignore this gibberish here. If I have pH minus pKa, then that means that all that's left on the other side of the equation is the log of the benzoate over the acid. So the log of the base over the acid is equal to the pH minus pKa. Well, I got the pH. They told me it has to be 4.3. I got the pKa. I calculated it before. And when I subtract those two numbers, I get a difference of 0.11. So the log of the benzoate ion, or base, over the benzoic acid is equal to 0.11. Get rid of a log by taking the antilog of both sides. Well, the antilog of base over acid would be found by taking the antilog of 0.11. That's super easy. Just take 10 and raise it to the 0.11. Hit enter. And that is rounded off the ratio that you need of your base to your acid. What we're saying is if you had enough, you could take 1.3 moles of benzoate and have it be proportional to 1 mole of benzoic acid. Or it could be 0.13 to 0.1. Any relationship that retains that or keeps that ratio that you've just calculated. So let's try a couple more until it becomes innate. If you look at the next problem, and again, just look first before you copy. Now we need a pH of 5 in a buffer. And they want to know if acetic acid and sodium acetate would be a good choice. When I go find the pKa from above, that was the pKa of 1.8 times the negative log of 1.8 times 10 to the minus 5. Maybe you've memorized that number by now too, I don't know. But I noticed that that's a pretty good choice because it's not greater than 1 or less than 1 from the magnitude of 5. Your choice is looking for a pKa that isn't more than 1 point above or below your desired pH. So that's a pretty good choice. So that combination will work. Using the equation that we had from the previous slide, the log of the base over the acid should be equal to pH minus pKa. So take 5, the pH, minus pKa, 4.74, and you get the answer 0.26. Now that's still the log of the base over the acid, so take the antilog of that number. 10 to the 0.26 equals 1.8. What that means is, and I've written it over here, you could have 1.8 moles of the base, the acetate, to every 1 mole of the acetic acid. Or if you needed to drop the magnitude down, which you guys will for your buffers, 0.18 to 0.10, and so on. So I hope you're seeing that this is pretty easy to do. It's not that bad. And now what I'd like you to do is truly stop the vodcast after you read this problem. Find the space on your handout where you can see I provided a spot for you to solve that problem. And shooting for a pH of 3.90 and knowing that the Ka of formic is 1.8 times 10 to the minus 4, would using formic acid and its salt make a good pair for this purpose. It should take you about a few minutes to make these calculations. When you're done, start the tape again and look at the solution that follows. How did it go? I found that the pKa of formic acid was 3.74, and that's pretty close, very close to 3.9. So first answer is yes. Formic acid and formate are a good choice. I took the pH minus the pKa and found the difference was equal to 0.16. 10 to the 0.16 is the antilog of that number. In my calculator was sitting a number of 1.4 rounded off. That means I would need 1.4 moles of the base formate to 1 mole of formic acid, or you could have 0.14 of formate for every 0.1 moles of formic. I hope you got that one right, because here is what your plan will be for block day. Each of you should have now received a handout that starts with this instruction. Prepare 100 milliliters of an acetic acid acetate buffer system with a pH of blank. I'll be filling in the blank the next day I see you. You are allowed to have 0.100 molar acetic acid and some solid sodium acetate before the lab, and to get the first stamp on your lab worth points. Using the examples above, you will show the calculations that you had to do to determine what is the correct ratio and amount of acid to salt, acetic acid to acetate, to achieve the correct pH. Then in block day, you're actually going to prepare the buffer and test the pH. So the other part of your grade for this lab is how close do you get to the correct answer? And don't get discouraged. Most people do great on this lab. Well, good luck with it. Until then.